welcome to the 21st lecture. We are studying stochastic processes and Markov, the topic Markov process. Under this topic, today we are going to study steady state behavior. Steady state behavior of Markov chains. Right. What is the steady state behavior of different states in a Markov chain? SS stands for steady state. We have already studied in previous lectures that Rij of n, it refers to the n-step probability of us of going from state I to j after n time steps. If initially the process is in state number I, the process is in state I initially. Initially means when the time starts at time t is equal to 0. The process is in state I. What is the probability that after passing n time steps, the process is in state j? This is we call Rij of n. But we have already studied that we can find for any given I and j. If we fix I and j, suppose to 1, 1 or 1, 2 or to any arbitrary values I and j, if we fix the values of these i's, I and j, and we vary n, we can plot a graph, and we plotted those graphs in one of our previous lectures for increasing values of n. And we see that for large values of n, they are going to show a kind of behavior we'll study shortly again. But studying their behavior for large values of n, studying of the behavior of Rij's by keeping the values of I and j constant and then varying n, this study is called steady state behavior of a state. Right. We have already studied that Rij's converge in previous lecture. They converge. In previous lectures we studied that suppose this is the way something goes on like R11. In one of our previous lectures we studied it decreases from a higher value and then settles at a lower value for increasing values of n. This is Rii, R11 of n. Right. But initial conditions do matter. If we have more than one recurrent classes, suppose in this example we have a recurrent class 1 and a recurrent class 2. But if somehow the process enters in RC1, recurrent class 1, it remains there. It cannot go out because there is no way it can go out and can enter into RC2 or in this transient state. But if it enters in this RC2, recurrent class 2, it remains there forever. Right. So these are some limiting conditions. In this situation, initial conditions matter. Right. In another kind of problems in another kind of Markov chains where we have only one RC, they may not converge. Converging means setting to a constant value as n increases. The asymptotic value is a constant value. Why? Because in this kind of chain where the probability of moving from 1 to 2 is 1, and from moving state 2 back to state 1 is also a 1. This means Rii, if you put I is equal to 1, this would be R11. If you put I is equal to 2, that would be R22 of n. They both would be 1 for an even n and 0 for an odd n. So the behavior would be a kind of oscillating behavior. So Rii, either it is R11 or R1 or R22, it is an oscillating behavior. So even in this problem, RIIs do not converge. So if we assume that we are working in a situation where we have neither this condition where we have more than one RCs, classes of recurrent classes of recurrent states, nor we have this situation. If we neglect these situations, then if we exclude the conditions above, which two conditions? This condition, and where we have an oscillating behavior, it's one RC, and it is a periodic RC, and this Markov chain where we have two or more than two sets of RCs, recurrent classes. If we exclude these two conditions, if we exclude the 2, let me write it 2. If we exclude these two conditions here, then in general, Rij of n is independent of I for large n. It's independent of I. Doesn't matter where do you start with. This means that R 1 1 and R 2 1 will converge in the same way, or will converge to a same value, because for regular Markov chains, excluding the above two conditions, Rij of n for very large values of n is independent of I, of this first subscript. It doesn't matter. R11 and R21 will be converging to the same value. Similarly, R12 and R22 will also be converging to the same value, because for very large values of n, Rij, the steady state probability, is independent of the starting point I. Right. And we have already studied in one of our previous lectures that R12 and R22 converge to the same value. In R11 and R21, they also converge to the same value. And we will explore this once again in today's lecture. Right. Then let's give this probability of xn is equal to j, since we are now independent of the initial condition, therefore of the starting point I. So we can write it probability of xn is equal to j, no matter where we started. Where did we start? Probability of xn is equal to j for large n. Let's give it another name, pi sub j, which is steady state probability of j. Steady state probability of j. Because it's independent of I, therefore we don't mention I here. The probability that the process is in state j at time n, we call it pi j, and we don't write n here because it is understood that n is very large. And we don't write I here. In this pi j, in this term, we neither write I nor n. Why? Because it's independent of n. Sorry, it's independent of I. Therefore, we don't need to write I here. And it is understood that this probability is for very large values of n. Therefore, we don't write n here. So it's pi j. Starting from anywhere, what is the probability of being at state j for an n that is very large. Steady state. Next we'll study steady state convergence theorem. Suppose we have a Markov chain with single aperiodic recurrent class. A single aperiodic recurrent class. This means RC1, this one, or RC2. And the class is aperiodic. This means we have already studied periodicity in our last lecture, that the chain is not like this, it's not periodic. A periodic chain is a one where we can draw a line and convert this into a set, and this into a subset, this into a subset. And the states in the subset, all arrows in one state are merging out and are entering in the next subset, states in the next subset. So if it is a single aperiodic, it's not periodic, contains a single recurrent class. There are no two or more than two recurrent classes. There is only one recurrent class of states, and it is aperiodic. Then we have some things to write here. We have some important information to write here. That is, for each state j, in the Markov chain, Rij of n is written as pi j for all I as n is very large. It's the same thing we have studied in the last slide, this one. Right. The example is, we studied this Markov chain a couple of lectures before, and we saw that R11 and R21, they converge to the same value, 0.75. And R12 and R22, they finally converge to the same value, 0.25. That's right. Using the formula based on recursion. The pi j in the theorem, the second part of the theorem says that the pi j's are the unique solution to this. If you want to find out pi j can be computed using the same recursion based formula we used for Rij's. If you remember, we studied this formula 3 or 4 lectures before. This formula is based on recursion, that to find n-step probability of going from state I to j is based on this. This was based like this. If we have started with state I and we want to end at time n at state j, then we used a recursion based formula that we apply the same Rij function to Rik function for n minus 1. We compute Rik instead of Rij, but for one lesser value than n, and this probability from transitioning from k to j at very next step is represented by the conditional probability in the Markov chain, Pkj. So this is we studied for n-term, for n-step probability in 2 or 3 lectures before. The same can be applied for these pi j's, because pi j is also a long-term steady state probability. It will be written as pkj and then pi k instead of pi j. And pi k's, if we add all pi k's, where k is from 1 to m, and m refers to, we have already studied that, m refers to all states in the state space. So here we have, in this case, in this example we solved earlier, we had only two states, 1 and 2. So this means that pi 1 and pi 2, the sum of these pi's should have been equal to a 1, and it is, because 0.75 plus 0.25 is a 1. So it is true for all Markov chains fulfilling this criteria. And then the last part of the theorem is that pi j, for any state j, pi j is 0 if it is a transient state. For example, this state number 3 is a transient state. So the long-term probability of staying at 3, it's obvious, is 0. We will not stay. If we will start from this state, we cannot stay here. We'll either move to 2 or to 4. So the probability of staying at state 3 in long term, it's not likely that we'll stay here. But pi j is greater than 1 for recurrent classes. Here we have two classes of two recurrent classes of recurrent states. So if we enter here, we will be there. If we enter here, we will be there. So pi j would be greater than 1. The long-term probability will be greater than 1 for recurrent states. That's all for this lecture. We'll continue studying Markov processes in our upcoming lectures. Thank you.